Uh, we have now seen all the chapters of the strength of materials section. Now we will solve problems of gate mechanical engineering, and we will solve it chapter wise. So this is the chapter 1 of gate mechanical engineering booklet. Now let's solve the problems. So the first question is a rod of length L. So question number 1. So it says there is a rod of length L, and diameter D. So this is the diameter D is subjected to a tensile load of P. So there is a load of P. Which of the following is sufficient to calculate the resulting change in diameter? So once the load is applied, we have to figure out what is the change in its diameter. So obviously, because in the diametral direction there is no direct load applied, so whatever change happens will be happening because of the Poisson's effect. So the material constants which are required, obviously the first option is Young's modulus E. Second option is the shear modulus G. Third option is the Poisson's ratio nu, and the fourth option is both E and nu, or both E and G. Sorry. So which of these four is the correct answer? So obviously, let's see how to get the stretch or the change of its diameter. So we know that change of length is obtained by PL upon AE. This is the formula for change of length, and the change in diameter is nu into change of length, because that's a lateral change. So we need both E and we need nu. So which of these answers is correct? Then obviously it is the option D. This is the correct option, because with G and E we can calculate the value of nu. Nu is or rather I'll say 1 plus 2 nu 2 times 1 plus nu is the ratio of E upon G. So if we know both E and G, we can figure out what is the value of nu from this equation, and from that we can calculate the value of delta D. So that answer is option D, or the fourth option, which is both E and G, or both Young's modulus and shear modulus. Now question number 2 and 3 are linked questions. So question number 2 is like this. There is a cylindrical container of radius 1 meter and wall thickness of 1 millimeter. So we have a container. This is the container, and it has radius of 1 meter. So this is the diameter, which is 2 meter, because the radius is 1 meter, and it has a thickness of 1 millimeter. This is the thickness of the container. This thickness is 1 millimeter, right? So this thickness is 1 millimeter. It has water up to depth of 2 meters. So this has water. Let's say this height is 2 meter. So this is water. So this height is 2 meters. This is the height, and this is filled with water, and it is suspended along its upper rim. So it is fixed to the, let's say, to the ceiling or something. The density of water is 1000 kilogram per meter cube. So that's the density of water. The value of G, the acceleration due to gravity, is 10 meter per second square. These values are given to us. They have been provided. The self weight of cylinder is negligible. So now the formula for hoop stress in thin-walled cylinder can be used at all points along the height of cylindrical container. So now we know that the hoop stress, sigma hoop, is given by PR by T. That's a hoop stress value. and the radius of this cylinder is 1 meter because the diameter is 2. It's given that the radius is 1 meter. So the first question, the question number 2 out of these 2 linked questions is the axial and circumferential stress sigma A and sigma C experienced by the cylindrical wall at mid depth, which means at this height, this level, at this location, what is the axial and the circumferential stress, which means that axial and hoop stress, what are those values? So for that point we have to first figure out what is the pressure there. So the pressure at height 1 is given by rho into G into H, which is nothing but 1000 multiplied by 10 multiplied by 1. So that's around 10,000 Pascal. That's the value of stress at that level. So the hoop stress is nothing but the pressure 1 multiplied by R upon T. So this pressure 1 is 10,000, radius is 1 meter divided by thickness is 1 millimeter, which is 10 to power minus 3 meter. So that gives me 10 to power 4 multiplied by 10 to power 3, 10 to power 3. So that's 10 to power 7 Pascal. That's the value. Okay, 10 to power 7 Pascal is nothing but 10 megapascals. It is 10 into 10 to power 6 is 10 megapascal. So this is the hoop stress, and the axial stress is nothing but 1 upon 2 of hoop stress. We know this number, so we just give it is 10 upon 2 is 5 MPa. So which is the answer? The answer is the first option A is 10 and 10 MPa. That is not correct. The second option is 5 and 10 MPa. That's the right answer, because the first one is axial stress, so this is this, and the second one is 10 to power 7, so this is that. Option C is 10 and 5. Those are inverted because 10 is the hoop stress, and the fourth option is option D. It is 5 and 5 MPa. Obviously that is also wrong, so this is the correct option, option B. So option B is 5 and 10. So that's the right one. Now what is question 3? Question 3 is the second linked question for this figure. If the Young's modulus and Poisson's ratio of the container material are 100 and 0.3, 100 GPa and 0.3, so we know that the E value is 100 GPa and nu is 0.3, right? Respectively, the axial strain in the cylindrical wall at mid depth is, what is the value of that? So what is the axial strain at mid depth? Let's take a simple element. So this is the axial direction, this is sigma A and this is sigma hoop for this problem, correct? So in this case we know that the axial strain epsilon will be equal to sigma A upon E minus nu sigma H upon E. That's the value of axial strain. So if I solve for this, I get sigma A is 5 MPa divided by 100 10 to power 3 MPa, because we have to convert E to MPa, minus 0.3 into this is 10 upon 100 10 to power of 3. So if I solve this equation, what do I get? Yeah. I'll write the equation once more. So epsilon A is nothing but sigma A upon E, or rather I'll say sigma axial upon E minus mu sigma hoop upon E. So if I solve for this, I get 5 MPa divided by 100 into 10 to power 3 MPa minus 0.3 into 10 upon 100 into 10 to power 3. So I just take this out. This 100 into 10 to power 3 is out, so it becomes 5 minus 0.3 is 3. 5 minus 0.3 into 10 is 3, so that's 2 upon 100 10 to power of 3. So that's the value of strain. Let's see which option is correct. Option A is 2 into 10 to power minus 5. Option B is 6 into 10 to power minus 5. option C is 7 into 10 to power minus 5, and option D is 1.2 into 10 to power minus 4. So obviously A answer is correct. This is A. This is 2 into 10 to power minus 5, because this is nothing but 2 into 10 to power minus 5. So option A is the right option. Now let's see what is question 4 in the booklet, Mechanical Engineering. A steel rod of length L, this is question number 4. Yeah. A steel rod of length L and diameter D is fixed at both ends and is uniformly heated to a temperature rise of delta T. So we have a steel rod like this. Its length is L. And its diameter is D. Now this rod is heated to or subjected to a temperature increase of delta T. That's the temperature increase. Young's modulus is E and coefficient of thermal expansion is alpha for this material. So what is the thermal stress induced in the rod? So how do I find the thermal stress? So I know that the thermal strain because of delta T is given by alpha into delta T. That's the strain. So the thermal stress is nothing but E into alpha delta T. Now let's see which option matches. So option A is 0, option B is alpha delta T, option C is E alpha delta T, and option D is E alpha delta TL. So those are the 4 options which we have been given, and obviously option C is right. But see, in this case there is a very easy way to figure out what is the answer without even solving the problem. We have to see what is the dimension of the answer, all the answers which are provided. So what is that we are supposed to find out? We are supposed to find out a stress. So stress has a dimension of Pascal or megapascal. So let's see. The first option is 0. Here we do not know what is the option, what is the answer, but we know definitely that it cannot be 0. It is fixed. The bar is fixed at both ends. So it will have certain stress. It will have no strain, but it will have certain stress. So this option is wrong. Option B is alpha delta T, that is dimensionless quantity. Obviously that is wrong answer because it has to have dimensions of stress. So this is also wrong. Option D doesn't have dimensions of stress again. This has dimensions of force per unit length because it is multiplied. It has E and L multiplied. So E has dimension of stress and L doesn't have L has dimensions of length. So the dimension doesn't match to the stress dimension. So obviously answer is E alpha delta T. So we know without even solving the problem, we know that the answer is E alpha delta T, which is option C. Now question number 5. Question number 5 is 200 by 100 by 50 mm steel block is subjected to hydrostatic pressure of 15 MPa. So we have a solid bar of 200 by 100 by 50. These are the dimensions of the solid steel block, and it is subjected to hydrostatic pressure of 15, which means everywhere we have a compression of 15 like this, 15, 15 and 15 and all that. Okay, so we have to find out what is the and also the Young's modulus is given as 200 GPa and the Poisson's ratio is given as 0.3, right? So these have been again provided to us. So we know that to get the answer here, we need to get the bulk modulus of the material. Now the bulk modulus of the material K is given by E upon 3 times 1 minus 2 nu. That's the bulk modulus of the material. Now bulk modulus I can calculate a bulk modulus in this case, which is equal to 200 by 3 times 1 minus 2 into 0.3. That's the value of bulk modulus, which is nothing but 200 by 3 into 1 minus 2 into 0.3 is 0.6, 2 into 0.3 is 0.6, 1 minus 0.6 is 0.4. So if I just divide this becomes 2000 by 12, which is nothing but I divide by 4, so I get 500 by 3. That is the bulk modulus of this of steel, and the change of length is nothing but the original length multiplied by the stress upon bulk modulus. So here it is 200 into 100 into 50, that's the volume, multiplied by stress is 15 MPa. So this is 15 MPa divided by K. K is 500 by 3 GPa. Correct? So I just do the calculation. So this this 3 goes up. So I have 200 by 100 by 50 into 3 into 15 divided by 500 into 1000, because I have to convert GPa to MPa, right? So this becomes MPa upon MPa, cancels out. So this, if I solve, I will get, I can divide this 500 like this and this 1000 like this. So in the end I will have 2 into 3 is 6 into 15, 90 millimeter cube. So that's the answer, which is nothing but option B. So option A is 85, option B is 90, option C is 100, and option D is 110. So answer is option B, which is 90. So let's see what is question number 6 now. Question number 6 is, a steel bar of 40 by 40 square cross section is subjected to an axial compressive load of 200 kilonewton. So we have been given a steel bar of square cross section. Each of the side of the square is 40. So this is 40 and this is 40. Correct? So this is the problem, and it is subjected to a compressive load of 200 kilonewtons. So there is a compressive load like this of 200 kilonewtons, and the length of the bar is 2 meters. So this is 2 meter from here till here, and the value of Young's modulus is 200 GPa. So what is the elongation is what we are supposed to find out. That's a straightforward question. Actually, we don't need to do anything but just simply apply that delta L is P is 200 into 10 to the power of 3 Newton divided by area of cross section, which is 40 into 40 millimeter square. See, it's in millimeter, into length is 2000 millimeter divided by E value is 200 into 10 to the power of 9, or 200 into 10 to the power of 3 Newton per millimeter square, because it is Newton per millimeter square is MPa. So because we are using Newton and millimeter, so it is just 200 into 10 to the power of 3. So it's now straightforward. We have to just solve this problem. So in this case, I can simply take this 200, this 200 and 10 to the power 3 will divide this, becomes 10 to the power minus 2. So it becomes 200 into 10 to the power of 3, and 10 to the power minus 2 will become 200 into 10 divided by 1600. Sorry, 1600. So this becomes 2000 by 1600. What is the value of 2000 by 1600? It is nothing but 5 by 4 or 1.25, because it is, this gets cancelled out. 20 by 16 is nothing but if you divide by 4, it is 5 by 4. So it is 1.25. So the answer, the options given are A 1.25, B is 2.7, C is 4.05, and D is 5.4. So the answer is A 1.25 millimeter. That's the answer. Now let's see what is question number 7. Question number 7. This is question number 6. The previous one which we have just solved is question number 6. Now question number 7. A bar having a cross-sectional area of 700 millimeter square is subjected to axial loads at the positions indicated. So there's a bar like this. It has area of cross-section of 700 millimeter square. So I just write it here. It is area is equal to 700 millimeter square. It is subjected to, see the now this problem is more of a free body diagram problem. So this bar is divided into 3 segments. These are the 3 segments. This segment is called PQ. This segment is QR, second one. This is P. And the third segment is R and S. So, and at segment P or the end P, we have a tensile force of 63 kilonewton. At segment Q, we have, rather let's say left acting force of 63 at P, right acting force of 35 kilonewton at Q, then again right acting force of 49 kilonewton at R, and a compression or left acting force of 21 kilonewton at S. So we are supposed to figure out what is the value of stress in QR segment. So in this central segment, this portion, what is the stress is what we are supposed to figure out. So let's draw the free body diagram of this. So the 3 segments can be taken separately, and in this PQ we have 63 kilonewton acting here. So to balance out, this must be 63 acting here also. Now let's take QR. So QR is like this. This is Q, this is R, and we know that at this location the net force is 35 because it is given to us. This is 35 net force. So obviously when I apply a force here, at this location I am applying a force such that the net force becomes 35. So obviously how the net force will become 35, there is a 63 force acting in right side direction. So a force in left side of 63 minus 63 acting this way minus a force of some x acting this way is equal to 35 acting this way. This is what we are doing. So the x will be equal to 63 minus 35. So this will be nothing but 28. So we have to have a force which is actually acting like that. This is the force 28 here. Obviously to balance out, this has to be 28 this side also. So we know that the central segment of QR is having a force of 28, tensile force of 28. Now let's see whether this balances out from the other side also. So I take the third segment. This is a 21 force here which is given, and we know that the net force is 49 this way. This is 49 here. 49. It is provided to us. So how will it become 49? When there is a force which is 28 already acting plus 21 more, which is nothing but balancing force of 21 here. So obviously this 28 is the right answer. So when the force is 28, the stress is 28 by 700. That is the value of the area of cross section, and this is kilonewton and this is millimeter square. So this is 28 into 100 into 1000 Newton by 700 millimeter square. So this is 700 and this is 28. Now this can be easily solved. This 100 cancels out these two zeros, and 28 by 7 is 4, so that becomes 40 MPa. That's the answer. So let's see what are the options. Options are option A is 40, option B is 50, option C is 70, and option D is 120 megapascals, all of them. So the correct answer is A, 40. Now question number 8. Yeah, question number 8 is, a uniform slender cylindrical rod is made of a homogeneous and isotropic material. The rod rests on a frictionless surface and the rod is heated uniformly. So please remember the key line here. The rod is resting on a frictionless surface, which means there is no constraint on the rod. It is just resting on the frictionless surface. So there is no friction, which means that when the stretch or compression happens, nothing stops the rod from freely compressing and stretching. The rod is heated uniformly if the radial and longitudinal thermal stresses are represented by sigma r and sigma z respectively. Then, so there's a rod like this, and it is resting on a frictionless table, and there is a delta T happening on the change of temperature of delta T, some heat, some temperature change, and sigma r and sigma z are the two stresses which are along the diameter and the length of the rod. So what are the values of sigma r and sigma z? So what are the options given to us? Option number A, or option A is sigma r equal to 0 and sigma z equal to 0. That's option A. Option B is sigma r is not equal to 0 and sigma z is equal to 0. Option C is sigma r equal to 0 and sigma z is not equal to 0. That's option C. And option D is sigma r is not equal to 0 and sigma z is not equal to 0. So these are the four options. Obviously, because there is no constraint, there cannot be any stress. So option A is right, which means that there is no stress either in radial direction or in longitudinal direction. Let's see what is problem number 9. Yeah, problem 9 says, in terms of Poisson's ratio, the ratio of Young's modulus and shear modulus of elastic materials is given by. So we know that G is equal to E upon 2 times 1 plus nu. That's the value of relationship, or that's the relationship between the shear modulus and Young's modulus of a elastic material. So that gives me E upon G is nothing but 2 times 1 plus nu. So now the answers or the options are A, 2 times 1 plus nu, B, 2 times 1 minus nu, C, 1 upon 2 1 plus nu, and D, 1 upon 2 1 minus nu. So obviously the answer is A. It's 2 times 1 plus nu. Question number 10 is question number 9, right? So in question number 10, the figure below shows a steel rod of 25 millimeter square cross-sectional area. Right, so the figure below is like this. There is a large bar, or a long bar rather. It has again 3 segments, one segment, another segment, and a central segment. So this is called K, and this is called L, this is called M, and this is called N. These are the 4 segments of the, or 3 segments of the bar. Length KL is 500 from here to here, and length MN is 400, and the total length is 1700. from here till here. These are the things which are provided to us. They have been given. Now at K there is a left side force of 100 Newton. At L there is a right side force of 250 Newton. At M there is a left side force of 200 Newton, and at N there is a right side force of 50 Newton. These have been again provided to us. What we are supposed to do, we have to find out the total change in the length of the load rod due to this particular loading. Now obviously the load is not uniform across the segments, and the lengths are also not same, so we have to find out the change in length of each segment separately and then add up the three changes of lengths. That will be the total change. So how do I solve this problem? So I take KL first. So what is the load in KL? KL is like this. It has 100 here. To balance out, 100 must be here also, and the area of cross section is 25. So the stress in KL is 100 upon 25 MPa, because it is Newton by millimeter square. So that is 4 MPa. The value of E is 200. So the strain in KL is 4 upon 200 10 to the power of 3, which is nothing but I'll say it is 4 upon 200 into 10 to the power minus 3. That's the strain. So the change of length of KL is nothing but its original length LKL multiplied by strain. So that is equal to, or epsilon KL. So that is equal to 4 by 200 into 10 to the power minus 3 into L. L is the length of that is 500. So this way we can write the equation for the other two segments also. This is nothing but PL upon AE for all the three. So the total length, or so the change of length of LM similarly will be equal to the P in that. So how do we find out P in that? So first we have to find out the P. So I take the segment LM again separately, and obviously there is 100 Newton acting here. So to balance out, there must be a compression of 150 acting, and this side also there is a compression of 150. And for this case, for MN, there is a compression of 50, and there is a compression of 50 from this side also. So we know that these are the three loads now. So sigma, or rather let's say delta M LM will be equal to the force in that, which is minus 150 upon 25. That's the area of cross section, into E. E is 210 to the power of 3 into its length. Now what is the length of LM? The length of LM is 1700 minus 500 minus 400. So that is equal to 800. And similarly delta MN is equal to, the force in that is minus 50 divided by 25 divided by E. E is same for all of them, into length. Its length is 400. So now total change is delta KL plus delta LM plus delta MN, which is nothing but the force in KL. Force in KL is 100 into its length is 500, plus the force in LM minus 150 into its length is 800, plus force in MN is minus 50 into its length is 400. Area and E are equal for all of them, so that becomes 25 into 210 to the power 3. So I solve this problem. Now its a solution is just algebraic. It's very easy to do. So this is 50,000 and 120,000 and 220,000, right? So this is I take out 100 from here, 100 from here, 100 from here, and this 100 from here. So it becomes 500 minus 1200 minus 150 into 8 is 1200 minus 50 into 4 is 200 divided by 25 into 2 into 10 to the power 3. So that is equal to, now this is 12 to 14 minus 5 is 900, minus 900 rather, divided by 25 into 2 into 10 to the power minus 3. So this is 50 and I do this calculation, so this becomes 900 by 50 is 90 by 5 is 18. That's the change of length. So it is, let's see what are the options which have been provided to us. Answer A is 1 micrometer. Answer B is minus 10 micrometer. Answer C is 16 micrometer, and answer D is minus 20 micrometer. But our solution doesn't match, so we have to check what has gone wrong. So I check the solution again. It is 100 into 500. That's right, 100 into 500 plus minus 150 into 800. Is that right? 917 minus 9 is 800, right? And minus 50 into 400. So it is 500 minus 15.8 is 120. That's right. And 50 into 4 is 200. So that's also right. So this becomes and the area of cross section is 25, and the Young's modulus is 200, so that's also right. So just let me check the calculation once more. Oh, I think I took this force wrong, sorry. Yeah, this is 50 is tensile, sorry. So this becomes plus 50 actually, so this becomes plus, so this becomes 1200 minus 500 minus 2700, so this becomes minus 500 actually. I'm sorry about it, I did the calculation wrong. So that becomes minus 500 10 to the power minus 3 upon 25 into 2 is 50, so that becomes minus 10, so that becomes minus 10 micrometer. So B answer is wrong. So I'm sorry for the goof up, it is option B. So see, please keep in mind that you have to check you have to draw the correct free body diagram. You shouldn't make such kind of mistakes.